Have you ever wondered how your phone just works? Or how GPS in a car knows exactly where you are, down to the street corner? It seriously feels like magic, doesn't it? Well, it's not. It's an invisible force, and today, we're gonna make it visible. I mean, just think about your day. You've probably already used Wi-Fi, sent a text, maybe you've flipped through channels on your TV. Every single one of those things. They all rely on these invisible signals that are just zipping through the air all around us all the time, carrying information in a blink. So, what is it? What's this invisible stuff that connects your phone to a satellite that's thousands of kilometers away in space? What's the secret? Well, it's time to decode this mystery. Let's get right into it and break down what's really going on. And the answer is electromagnetic waves, or, EM waves for short. These are the absolute unsung heroes of our modern connected world. So, what in the world is an EM wave? Well, the easiest way to think about it is like a ripple in a pond. But instead of water, an EM wave is a ripple in space itself. It's made of two parts that are linked together, an electric field and a magnetic field. And they're vibrating, they're oscillating. And as they travel, they carry energy with them. Okay, now look at how this thing moves. You've got the electric field in red, bobbing up and down. Then you have the magnetic field in blue, wiggling side to side. But the whole wave is moving forward, away from you. See how the vibrations are at a right angle, or perpendicular to the direction of travel? That's what makes it a transverse wave. It's a key idea. And being transverse is just one of their shared family traits. All EM waves, and I mean all of them, follow the same rules. They can travel right through the total emptiness of space, which is a good thing, otherwise we wouldn't get any sunlight. They don't have a charge. They always transfer energy. And they all travel at the exact same unbelievable speed. And that speed, it's 300 million meters per second, the speed of light. That is ridiculously fast. It's fast enough to zip around the entire Earth more than 7 times in a single second. That's it. That's the universe's ultimate speed limit, and every EM wave hits it when it's in a vacuum. So, wait a minute. If they all travel at the same speed, how are they different? What makes a radio wave different from, say, an X-ray? Well, that brings us to the family portrait of EM waves, the electromagnetic spectrum. Now, it's really important to think of the EM spectrum not as a list of separate things, but as one single continuous rainbow. It's all the same stuff, just with different properties. On one end, you have these really long, stretched out, low-energy waves. And on the other end, you have these super short, scrunched up, high-energy waves, with everything else you can imagine in between. And this right here, this is the most crucial relationship you need to get. It's an inverse relationship. The longer the wavelength, that's the distance from one peak to the next, the lower its frequency and the lower its energy. Some radio waves are literally as long as a football field. But on the other end, the shorter the wavelength, the higher the frequency and the higher the energy. We're talking gamma rays that are smaller than a single molecule of water. It's that simple. Long wave, low energy. Short wave, high energy. Now, this huge range in energy and wavelength is exactly what makes the spectrum so unbelievably useful to us. So let's dive into the fun stuff and see how we've figured out how to put all these different waves to work. We're going to take a walk across the entire spectrum. We'll start with those long, low-energy waves and work our way all the way up to the really high-energy ones. Okay, starting at the long end, you've got radio waves. These are what bring music and talk shows to your car radio, but they're also used in those RFID tags in stores. Now, shorten the waves just a little bit, and you get microwaves. And yeah, they heat your leftovers, but they do so much more. They are the backbone of your Wi-Fi router, your cell phone signal, and the GPS that gets you where you need to go. Next up, moving along the spectrum, is infrared. You use this every day, that remote control for your TV. When you press a button, it's sending out a little pulse of infrared light. And because anything that's warm gives off infrared waves, we can use special cameras for thermal imaging to literally see heat. Now, right in the middle of this enormous spectrum is this teeny tiny little sliver that we call visible light. It's amazing, but this is the only part our eyes have evolved to see. It's obviously essential for life on Earth, think photosynthesis in plants, and we've even harnessed it to send huge amounts of data at, well, the speed of light through fiber optic cables. Okay, now we're cranking up the energy. We're getting into the more powerful side of the spectrum. First up is ultraviolet, or UV light. The same kind of energy from the sun that can give you a sunburn can be concentrated to sterilize medical tools. And if you crank up the energy even more, you get X-rays. They're so powerful they can pass right through your skin and muscle, but get stopped by your bones, which is how we can see right inside our own bodies.
So you can see the pattern, right? As we move up the spectrum, the energy gets higher and higher. And this leads to a really important question, and a critical difference that we absolutely have to talk about.
If higher frequency means higher energy, can that energy actually be harmful? The short answer, yes. Some of them absolutely can be. But to understand why, we need to draw a line in the sand and divide the spectrum into two groups.
And here is that dividing line. Everything on the lower energy side, radio waves, microwaves, infrared, and visible light, is called non-ionizing radiation. These waves just don't pack enough of a punch to knock electrons off of atoms. But once you get to the higher end of UV and all of X-rays and gamma rays, you're in the zone of ionizing radiation. These waves have enough energy to do just that, to literally knock an electron out of its orbit.
Now, I know the word radiation can sound pretty scary, but let's put things in perspective for a second. Take a look at this. The vast majority of the ionizing radiation we're exposed to isn't from cell phones or power lines. It's from completely natural sources. It comes from radon gas in the ground, from cosmic rays from space, and even from the food we eat. So why does this ionizing thing matter so much? Well, think of those high-energy waves like tiny invisible cannonballs. When one of them smacks into an atom inside one of your cells, it can blast an electron right off. That creates an ion, an unstable atom, and that instability can cause a chain reaction that damages or even kills the cell. That's why we wear lead aprons for X-rays and put on sunscreen at the beach. So, there you have it. From radio waves that let us talk to people across the planet, to X-rays that let us see our own bones, we have learned to master this incredible, invisible force. It really makes you wonder, doesn't it? What's next? What part of this amazing spectrum is just waiting for us to unlock its secrets and change the world all over again?